Hello, good morning, everybody. Can you hear me and can you see my screen? Anyone? Yes, sir. All right, thank you. Let's take a moment to scan attendance and then we will begin with our class. Okay. All right, good morning, everybody. Wow, it's early in the morning. Attendance not so good today. 1, 2, 3, 4, 6, only 7 of you. But no matter how, we will still continue with our class, and hopefully those who are not in the class will catch up real soon. Okay, right, let's continue from where we left off last class. So in the last class, I've explained to you that we are right now in topic 7, and topic 7 is very different from the rest of the topics, in which all our previous topic, we talk about combinational logic, we talk about logic gates. And the difference between those are logic gates only consider what you give it right now, input, and the output. It does not consider all the past input, right? And that is different in topic 7 onwards. Topic 7 is what we call sequential logic. And in sequential logic, we care about what is the current state, current input, current output, and we also care about what is the previous one. Okay, so that is the difference. So this is a fundamental concept on how memory is created. Okay, in computer systems, memories are created using sequential logic. So we talk about a few things. This is the introduction. Sequential logic. Yep. So the output depends on present input as well as the past input. So this is a key point that we have considered. Right, so this is one example of a sequential logic. This is a classic example, and counter. So counter is a classic example because in order for the counter to increase the number, it has to know what is the current number, right? If the current number is 0, then it knows that, okay, the next number I'm going to increase it to 1. And if current number is 1, then you know that the next number is going to be 2. So a counter needs to keep track what is the current number and what is the past number, so that it knows what will be the next one. So that is an example of a sequential circuit. Counter, and yeah, this is a example. And we also looked at two types of sequential circuit that we will learn in this course. Is they are latches and flip-flop. So in the last class we've covered latches. So hopefully by now you know what are latches, what are they used for, how they work. In today's class we're going to talk a little bit about flip-flop. Okay. So yeah, we explained a great deal about latches, how they work, and we've gone through the truth table of two latches, namely SR latch. So SR latch, remember that we have 4 states. So when you give it the value of 0, 0, it's a no change state. Give a value of 0, 1, it's a reset state. You give a value of 1, 0, it becomes a set state, and you give a value of 1, 1, this is known as an invalid state. Okay. So in a no change state is not going to change the output. So whatever output that is existing right now, in the next output is going to stay the same. So if you give it a reset state, the output is going to be changed to 0. Okay, Q is going to be 0. If you put it in the set state, Q is going to become 1. Okay, and this one is an invalid state. So we try to avoid this giving two values of 1 into a SR latch, because this will give an error at the output, and the output is in an indeterminate form. Okay, it can be 0, it can be 1, it can be 0, 1, or it can be bouncing between the two values 0 and 1, like that. So it's not fixed. So that's why we put a X over here. That's SR latch. And I believe we also talk about the other latch, which is D latch. Let's see, let's delatch. Okay, we also talk about delatch, and delatch is much simpler. So delatch is a latch that's supposed to solve the problem of SR latch, remember? So what a delatch does is that it's a SR latch inside, but in between it's got a NOT gate, so that at one point it makes sure that S and R does not have a same value. Okay, so that is what happens. If D is 0, the output will be 0. If D is 1, the output will be 1. So that is a D latch, or it's a data latch. Okay, that is how it works. And we also saw that we can actually plug in an enable also into D latch and also an SR latch. So if you have an enable, it's called a gated D latch or gated SR latch when you have the enable. And of course, if you have the enable, then your table will need to have also this enable value. Okay, so as you can see over here, if your enable is 0, then it doesn't matter what's the value of D. All right, so that's gated D latch. And we also went through this very important timing diagram in the last class. So this timing diagram was important, so hopefully you understood what I talked about in this timing diagram in the last class. So if you think you're still not clear, feel free to watch the recording on specifically on this timing diagram, because this encapsulates what I talk about in the latches class. All right, so if you still cannot get from watching the recording, please feel free to drop me a message, and I'll try to explain it in another way that maybe you can understand better. Okay, so that was what we did in the last class, and we also did some research homework. So hopefully you guys have done this research homework, how to researching about these two additional latch, T latch and JK latch. So by the end of today's class, we'll have a quiz on these two latches, right? Okay, so coming back over here to this simple diagram over here. So we talk about memory. In memory, there's two ways we make we construct a system with memory. One is by using latches, and the other one is using flip-flops. In today's class, we are going to cover this one, this topic, flip-flops. All right. So let's take a look at what are flip-flops. So in latches, remember that we have, let's say this is a SR latch, SR latch, Q, and this is a Q bar. So let me draw that. And in the SR latch, we can have an enable. Remember, so we can have enable. So usually it's drawn like this, enable. And the difference between flip-flop and SR latch is at this point over here. So instead of having an enable over here for SR latch, an SR flip-flop will have this enable replaced by another input called CLK, or in short, that's CLK in short. The long form is called clock. Okay, so instead of having enable, we have a clock as we call it a trigger source. So let's take a look at what is clock actually. A clock is nothing but a square signal. Okay, a square signal. A square signal looks like this, or it's a square wave. So if you have a square wave, this one will be logic 0. Over here will be a logic 1. So this square wave is known as clock. Why is it that we call this a clock? So let me give you a simple analogy, right? A clock is used to synchronize all the circuits in a computer. Okay, so for example, a good analogy is this. Say I make an appointment with you. So I say that, okay, we have class at 8 a.m. Let's join the Teams meeting room at 8 a.m. So how do you know when it's time to join the meeting, right? So we refer to something as a clock. So I have my clock, you have your clock, and when your clock shows 8 a.m., then it's time to join the class. So that is how clock works in the circuit as well. So all this flip-flops, they have a clock, and this clock is usually shared by all the flip-flops so that their timing can be synchronized together. So we'll talk about this timing and synchronization like in the next chapter. But for now, just understand that clock is a signal that is used to synchronize things. And in flip-flop, clock is used as a enable. So usually this clock or the square wave is applied to this pin over here. Okay, so if you're doing a digital logic lab, you might have used this clock signal in the lab, but maybe you're not aware that there was a clock signal. Okay, so the difference between flip-flops and latches is latches, they work on enable. If you put the enable high, then it will work. If you put enable low, it will not work. Okay, or the other way around, if it's an active low enable. But for flip-flop, it works only when you have this clock signal. So a clock signal looks like a square wave. Okay, this is what a typical clock signal would look like. A square wave is just a repetition of going from 0 and then to 1 and then to 0 to 1, 0 to 1, and so on and so forth. All right. So in a square wave signal, you have several components. Okay, you have several components, and they are high, they're low, and they are positive edge and negative edge. So let's talk about the high and low first. So this is the straightforward one. So these are the low part of the signal. The low part is where the clock goes to logic 0. These are the low level. Okay. What about the high level? High level is the opposite one. So it was when the clock is at the high, logic high. So logic high, logic high, logic high. So there are two new elements that I want to introduce to you guys today. That is, a clock also have a positive edge and a negative edge. So what is a positive edge? So a positive edge is the transition when the signal goes from logic low to logic 1. And it's exactly this vertical bar over here. This is a positive edge. And this is another positive edge. And it's another positive edge. Okay. Usually we draw like an arrow like that over here at the positive edge to indicate that the logic goes up. So positive edge is also a positive edge. All right, and negative edge is the other way around. It is when the signal goes from 1 to 0. So negative edge is over here, 0 like that. These are the negative edge. Okay, negative edge. Okay, so what is the difference between flip-flops and latches? Right, so here is a clearer difference on the flip-flop and latches shown on this signal. So for latches, they function when your enable has a level of 1, like here. Okay, this is assuming that this is an active high enable latch. Okay, they function when on the green region over here. Okay, and if it's level 0, it does not function. But for flip-flop, okay, take note over here, for flip-flop, it will function only at the edges over here. Okay, edges. So it will function at this vertical line like that for positive edge. Okay, or it can also function on the negative edge. So we'll talk about both of these cases. All right, so this is what we call a trigger source. So for latches, the trigger source is the what we call level trigger. Okay, level trigger, which means that the trigger is at the level, it's either level 0 or level 1 or level 0. For flip-flop, this is called edge trigger. Okay, edge trigger. Okay, so instead of functioning, the flip-flop will only function when you have an edge. It can be a positive edge going up like that, or it can be a negative edge going down like that. Let's look at this timing diagram. Okay, this timing diagram is an important one, so pay attention, pay close attention to this one. So this one is the timing diagram that we covered in the last class. Okay, right, so I've talked about this in the last class. Later on, we'll see what's the difference. So this is the timing diagram of a trigger happens when enable goes to 1. All right, so take a look over here. The flip-flop functions only when, okay, change this in color again. Yeah. This is not flip-flop, this is a gated D-latch, sorry. So this gated D-latch only works when you have a enable high over here, enable high over here, enable high. Okay, so whenever you have this enable high, it's going to look at what is the value, the current value at this point when the enable is high. So if the enable, if D is 1, then it's going to change the value of the output to 1. Only within this time when the enable is high. Once the enable goes to low over here, it does not work anymore. The latch does not work anymore. Okay, this is the latch, right? It's not the flip-flop, it's latch. I'm just going to highlight what's the difference. So if the enable is low over here, the latch doesn't work. So even though you change the value of D, the output is not going to respond to that change. Okay, so this is latch. It works on level high over here, and it does not work on level low over here. That's latch. All right, so for flip-flop, the trigger is not going to be at the level, it's going to be at the edge. So I'll show you another timing diagram over here later when we have this edge trigger. All right, so let's talk a little bit about trigger. So there is a positive edge, a negative edge. We talked about that just now. All right, so positive edge is this one, negative edge is the other one. So latches rely on level trigger. This is level high. This is a low level or logic low trigger, level trigger. Okay, so that is one key difference. So how does a flip-flop look like? So this is how a flip-flop will look like. If you're in the digital logic lab, a flip-flop is, you know, as boring as this black chip over here, right? So it's got like 8 pins, and inside this is if you look at the schematic diagram, inside of this black chip over here, you typically have like multiple flip-flop, maybe sometimes 2 flip-flops, right? And so take a look at the clock. So the clock signal, typically you connect it to the enable. Okay, this is how we draw a clock signal. So let's say this is the SR flip-flop. This is how it will look like. This is Q and this is Q bar. Okay, so this is where you would connect your clock signal. So the clock signal is connected to this, used to be an enable pin. If it is a latch, there's an enable pin. So you connect your clock, this is a square wave, to your enable pin. Okay, so this is written as this. All right, so clock allows the change in flip-flop to be synchronized, right? And it can be rising or falling edge trigger. So also one thing that I'd like to highlight, if you see in the schematic diagram, this clock over here is drawn like this. This is a rising edge flip-flop. Rising edge flip-flop. The rising edge means the trigger is on the rising edge. It's the when the signal goes from 0 to 1, rising edge flip-flop. So if it's a falling edge flip-flop, the clock will have this kind of drawing. So it has a bubble over here. Okay, then you have a falling edge flip-flop. SR. I'm just putting an example here. This assuming it's a SR flip-flop. Okay, so it's drawn in this way: rising edge or falling edge. Okay, right. So this was what I was drawing just now: rising edge versus a falling edge flip-flop. Okay, so this is a rising edge versus a falling edge flip-flop. Excuse me. Right, so the difference over here you can see at the bubble, and you also have a D flip-flop. Okay, so let's talk about the difference between a D latch and a D flip-flop. Right, over here we have on the left we have a timing diagram of a D latch, and on the right over here we have a timing diagram for a D flip-flop. Okay, so this is a key point in today's class, so I'd like everyone to pay close attention to this diagram. So let's take a look at the diagram on the left first. So this is a D latch, and a D latch will only function when your enable is high over here. Okay, this is the region where your D latch will function. So whenever you get enable high on a D latch, what will happen is that at this point of time, exactly here, this D latch will turn on, and then it will take a look at what is the value of D that you supply at this point. The value of D is 0, so the output is going to reflect the same value as a D, so which is also 0. And then in the duration where the latch is on over here, and you decide to change this value to 1, and what happens at the output? The output will change, because D latch is just mirroring the input. Whatever the input is going to reflect at the output, right? So that is D latch. So however, once you turn off this D latch by giving an enable 0 over here, now this D latch doesn't care anymore what you give at the input. So even though you change the input over here to 0, now what happens? The output does not change, does not budge. The output is latched at this level. Okay, the output is latched at whatever value that it is currently on, which is 1 over here. Okay, and after that, if you decide to turn on the latch again, then it's going to respond to the input again. So once in this region, it's going to respond to this input again. So that's why you see over here, you see it changes the input changes, the output changes following the input. Okay, so at this point we see the latch is on, and then it's going to see what is the value of D over here, and then D is 0. It's going to change the output to 0. Okay, and then at one point you change it to the square like this, and the output is going to reflect that change. Okay, just up to this point, and then after that the flip-flop is turned off, and then no response again. Okay, so the period in which the latch functions is only when the enable is high. Okay, which is during this period, and during this period. Okay, that is gated D latch. Now, let's take a look at how is a flip-flop different than this. Okay, let's take a look at this diagram over here. So a flip-flop does not function based on the level, but a flip-flop function based on the edge. So how is it different? Okay, let's take a look at that. We still have this enable pin. Okay, so in flip-flop, this is written as a clock. Okay, so but I write here enable so that you can do a comparison over here. Enable, and this is also enable. So enable is given a square wave typically, but to highlight to illustrate this example on how the flip-flop works on the rising edge and falling edge, I'm just going to take this, not put square wave yet over here, but put a regular waveform over here. All right, but let's take a look at how this flip-flop functions differently compared to a D latch. All right, so this enable pin is given square wave like this. So the region in which the flip-flop functions is only here. It's only at one moment of time. This is at a rising edge over here. Okay, it's only a brief moment when the signal goes shot up from 0, goes up to 1. Only at that vertical line the flip-flop is going to function. Okay, let's take a look at this. So over here, you see enable gets a value of 0 in this region, right? The entire time when the enable is 0, even though the value of D over here changes from up to down and everything, your output will not respond to any of that. Okay, so the output stays just flat, 0. Okay, so once you arrive at this point when the enable goes up like this, it is a trigger to your flip-flop, and this is a positive trigger. Once you have this positive rising edge trigger, this D flip-flop is going to take a look. Okay, at this point of the trigger, what is the value of D? The value of D is 0 over here. So the output is going to also take a value of 0. So the output is 0 over here. So unfortunately, you cannot see the difference over here because the original output is 0, and then now it's also becoming a 0. So it's 0 to 0. There's no difference over here at the output. Okay, so after that, as we progress, now the clock signal gets a value of 1 over here. So does the flip-flop works at the value of 1 over here? No, it does not work. This is not a latch. If this is a latch, then this latch will still work over here, right? So even though right now the value of enable over here is a value of high level 1, at level high level over here. So you change the value of input over here, go up like that, the output is not going to respond because the flip-flop does not work. Okay, remember the flip-flop only works until it sees the next trigger, and the next trigger only happens over here. Okay, so as we progress over time, going forward over time, you can imagine this is the timeline, and we are going forward like this. And at the moment we arrive at this time over here, okay, then the flip-flop turns on, and then it turns on like that. It's going to see what is the value of at this point. So the value at this point is 0. Okay, and that value is going to be reflected over here. Okay, unfortunately, it's also 0, and it becomes 0. It's not you're not going to see a difference in the output. All right, and after that, the flip-flop just turns off. It just ignores everything. So even though you give a change in the signal like that, the output is not going to respond to that until we reach another trigger over here. So until we reach another trigger over here, so it's triggered, it's on again, and at this point of time, then we are going to, this flip-flop is going to see, okay, what is the value of the input at this point that is triggered? The value of input is 1. Okay, because the value of input is 1, then the output is going to reflect that 1 over here. Okay, and that is when the output changes. So what's the difference? So for a D-latch, the period when the latch function is longer. It is during this duration over here. Okay, this tree duration over here. But for a flip-flop, the period in which it functions is only at that brief moment. Okay, only at that vertical line, only at this vertical line where it has got the rising edge trigger. Okay, so that's the difference between a latch and a flip-flop. Okay, so we have a D latch and D flip-flop, and the concept applies also to other flip-flop. So you have SR latch, you also have SR flip-flop. So the same timing that applies, except the output value here might be different because SR flip-flop has got a different mode. Okay, so over here we are seeing this SR flip-flop. Okay, so this SR flip-flop is a positive edge triggered SR flip-flop. The diagram is drawn like this. Right, this is the block diagram, and this is a positive edge triggered flip-flop because it's drawn like this. If it's a negative edge, you would see a bubble over here. Okay, and internally, this is how it looks like. So it looks like here, instead of having a enable pin, we have a clock pin, and this clock pin would get the square wave value. Okay, so the way it operates, it's very similar to the latch. So it's got set state, it's got reset state. So in the set state, the Q becomes 1. In the reset state, this Q becomes 0. Q is the output, right? Okay, so let's take a look at some tables, how it looks like. Okay, so this is how the SR flip-flop positive edge truth table would look like. So let's take a look at 0, 0 over here. So if you give a value of 0 and 0 to the S and R pin, but you do not have a trigger in the clock. In other words, a clock is level either logic 0 or logic 1, then there's no trigger, then the output will not change at all. Okay, so the output Q will remain at Q. All right. So what if you change it the other way around? So you have 0, 1 at the output, at the input, and you give a trigger over here. So you give a positive trigger. Now it means that this flip-flop will start to work, and because it starts to work, it will refer which mode is this in. Okay, 0, 1 puts this into a reset mode. Okay, reset mode. Okay, so because this is in a reset mode, so reset mode makes your output to be 0. Okay, clear? And over here, the next one we have 1, 0 over here. So 1, 0 on the other hand, puts your flip-flop into a set mode. Okay, so puts your flip-flop into a set mode. So this one has a trigger. So set mode makes your Q becomes a 1. Okay, so similarly, similar to this SR latch, SR flip-flop also has got a weakness. So the weakness is that when you give both 1, the value of 1 to the S and R, so this is again an invalid state. Okay, valid state. Because on one hand, you're trying to go into set mode. On the other hand, you're trying to go into reset mode. Okay, so the output will be indeterminate. So it can be 0, it can be 1, it can flip-flop between those two values. Okay, so there is no specific output. So we try to avoid this situation with SR flip-flop as well. Okay, so again, I've attached like a cool link over here. So do check out this link after the class. This is a truth table for flip-flop, SR flip-flop. Okay, there's one more case that I didn't cover over here. So what if you have 0, 0? So what if you have 0, 0 over here, and then you have a positive H at the clock, positive H at the clock. So 0, 0 and positive H, which means this flip-flop is functioning. And which mode is this in? So this is in a no change mode. So no change mode means that whatever output that it has now, it will keep that. Okay, so this is if you give 0, 0 and you give a trigger to the SR flip-flop. Okay, so that is the truth table. So the other table that I'd like to introduce to you guys today is the characteristic table. So the characteristic table is slightly more detailed than the previous table that you see. So in a characteristic table, what you will find is that you have an input. Okay, sometimes you also have a clock over here, but I didn't draw this clock column. So I'm assuming that the clock is triggered in every single row. Okay, the clock has a positive trigger. Okay, and assuming this is a positive edge triggered flip-flop, SR flip-flop. Okay, so for simplicity, I'm just going to draw this. Just going to show this input, and over here is the output. So the difference is that the output has got the current output, so which is the output that you have right now, and the next output that is coming next. So it's written as Q bracket T, which is the current, and we have our next, the current Q and the next Q. So over here, let's take a look. If you have 0, 0, this is in a no change mode, and your current value is, your current output is 0. So your next output will be the same. You will keep the same value because 0, 0 is a no change state. So it goes from 0 to the next output is also 0. It's not going to change. Okay, so take a look at what's the difference. If you have 0, 0, okay, 0, 0 is a no change state again. But if your current output is 1, so the next output is going to stay at 1. It's not going to change anything because 0, 0 is a no change state. So from 1, it becomes it's going to keep that value of 1. Okay, so now, so over here we have another, this is two of this is a no change state. Okay, no change state. So over here we have we put a value of SR to be 0 or 1. So what state is this? This is a reset state. Okay, so these two rows are in a reset state. Reset state. So you have a reset state, and if your current value is 0, it's going to reset and make the Q 0. Okay, so reset means you are making Q equals to 0. No matter what the value of a Q you have currently, reset is going to make sure your Q becomes 0. Okay, so if your current value of Q is 0, it's going to make it a 0. If your current Q of value is 1, it's going to make it a 0. So that is what the reset state does. Okay, right, take a look at the next one. Next one is the 1, 0. So you have over here 1, 0. Two of these rows are 1, 0. These are the set state. So set state is the opposite of the reset state. So in a set state, what is going on is that you are making the Q to a value of 1. Okay, so this is what a set state will do to your SR flip-flop. So if your current value of Q is 0, it's going to make it into a 1. Okay, if your current value of Q is 1, it's also going to make it into a 1. So, right? So whatever value that you have currently is just going to make it into a 1 if you're in a set state. Okay, and the last two row is this weird looking weird state. So this is called an invalid state. Why is it called an invalid state? Because this is an SR flip-flop, and in SR flip-flop you don't want the value of S and R to be 1 together. So these two, they are an indeterminate state. So if you have a value of 0 currently, what's the next output? The next output you really don't know, or you don't care. So you cannot say the next output is going to be 0 or the next output is going to be 1. It can be either one. Okay, same thing over here. So that's why I put a X over here. So that is the characteristics table. So a characteristics table will outline, will give you all the possibilities. So it gives you possibilities of 0, 0 over here, and the current output is 0. And it also gives you the possibility of the same mode, but the current value, current output value is 1. Okay, so this is a characteristic table. All right, so let's take a look at, yes, this is one important diagram that I will highlight. It's a highlight diagram of today's class, so just pay close attention, and after this, after this diagram, then we will done with our class today. Okay, so this is a flip-flop. Flip-flop is a positive edge trigger flip-flop, and this is a timing diagram for it. So we have over here Q, we have S, we have R, and we have clock as usual. Okay, all right. So I'm not gonna talk about Q bar because Q bar is just the invert of Q. So to make things simpler, I'm just gonna omit this Q bar. But you can see that Q bar is just the opposite of Q, right? All right. Pay close attention to this one. Because this is going to make you understand deeper what's the difference between SR flip-flop and SR latch. Okay, so time we progress, let's say if you progress from left to right, okay? So we go from left and we go forward in time like that. Okay, so let's say we begin over here in the beginning of this timing diagram. So we have an initial output of 0. Okay, the initial output is 0. And the initial value of S and R, they are also 0. And the clock is 0 over here. So at this point of time, does the flip-flop work? The flip-flop does not work because it's not triggered yet. Okay, so the trigger only comes when you got a positive edge. So where's the positive edge? The first one is over here. So you progress over time. So let's say we progress, timing diagram goes forward like that in a vertical line. And the moment we arrive here, okay, now the flip-flop turns on all of a sudden. And then when it's at this edge, it's going to see, okay, what is the value of S and what is the value of R? So the value of S is 0. The value of R is also 0. So what state is this? So this is a no change state, right? 0, 0 is a no change state. So no change state means that the output will keep the output will just not be changed. Okay, there's no change in the output. Whatever value that you have at the output is just gonna keep it that way. So what's the value that you have at the output currently? The value that you have currently is 0, so it's gonna keep it at 0, no change. Okay, so that's how we get over here a value of 0. It's just gonna take whatever output that you have previously and put it at this dot. Okay, and after that, after this rising edge is over, throughout all of this time over here, does the flip-flop work? The flip-flop does not work at all. The flip-flop just turns off, goes to sleep, and does not respond to anything. So even though during this time you change this and you change this, there's a change in this value. Does the flip-flop work? The flip-flop does not work. The output does not respond at all to anything that you do to the input because the flip-flop does not work until that is you meet another rising edge over here. Okay, so this is another rising edge, and during this time at that very short duration of this rising edge, the flip-flop just turns on, and then when the moment this flip-flop turns on, it's going to see what is the value of S and R over here. Okay, so at this point of time, the value of S is 0, the value of R is 1. So what state is this? S 0, R is 1. This is going to put it into a reset state, right? So reset means you're making the Q to be 0. So at this point of time, it's going to take the output, whatever output it is, it's going to turn it into a 0. Okay, unfortunately, the output, the previous output is already 0, and then you got now your flip-flop turns it into a 0. So 0 turning into a 0. So in a timing diagram, you will not see a difference. If the previous output a 1, then it will drop to 0 at this point, right? So that is when this trigger happens, and this value, this puts into a reset state, and this one goes to 0. And after that, throughout all this duration, it will not work again. So the flip-flop goes to sleep again, turns everything off, does not care. Even though you change the value over here, even though you change the value over here, the flip-flop does not react to that change. The output just keep over there. So if it's 0, it's just keep it the same output until we meet the next trigger, which is this one, right? So until we meet this next trigger, and this next trigger is going to do the same thing. It's going to flip-flop turns on again. It's awake. Now it's going to see what is the input over here. What is the value of S? The value of S is 1. The value of R is 0. So what state is this in? Value of S is 1. This is going to put it into a set state. Okay. So set state, it means you want to make the value of Q to be 1, right? So at this point of time, it wants to make the value of Q to be 1. So, and the current value of Q is 0. So because this flip-flop goes into set state, this Q value shoots up to 1. So 1 over here, and then that's it. It's over. The flip-flop now turns off. It does not care anymore. Throughout all this duration, it does not care. It does not change the value. Okay. So, and until you are here again. So if over here, then you're going to see what is the value over here. So it's 0, 1. So 0, 1, this is going to be a reset state. Okay, so 0, 1 over here, reset state. Reset means you're going to make the value of Q to be 0. So at this point of time, you've got your value of Q, present value is 1, it's going to drop to 0 because at this point of time, it is in a reset state. Okay. And then it goes until it meets this another edge over here. So at this edge, you have a value of 1 and 0. So value of 1 and 0 is a set state. So set state gives you a value of 1. It goes to 1, then it goes over here. And until you meet the last trigger over here, the last trigger over here is get the set state again. So set state gives a value of 1. So it's no change in the output. Okay. So anyone has issue with understanding this timing diagram over here, right? So have you noted the difference between a flip-flop and a SR latch? Okay, so an SR latch functions when you have an enable high, okay, and a flip-flop functions when you have a trigger. In this case, it's a positive trigger, okay? So that is how it is different. Okay, so this is a simple exercise for everyone today. All right. So this is the SR flip-flop. So I'd like everyone to go back and do this exercise. And so the exercise will be determine the Q and Q bar output waveform for the flip-flop for the S, R, and clock over here as below. Assume that it is initially reset. Okay, initially reset means what? The initial value is S equals to 0, R equals to 1. This is the initial value, and the Q will be 0 because this is a reset state, initial value. So this is the beginning of your timing diagram. We'll need to have this value. So this is today's exercise, and I will put this exercise as one of your quiz today. All right. So in today's class, we've learned about flip-flop, and particularly we've learned about SR flip-flop today. In next week's class, I think we will cover briefly and into more detail on D flip-flop and T flip-flop, and we also have another brand new flip-flop. It's known as JK flip-flop. So I'd like everyone that go back today, look up on this flip-flops, D flip-flop, T flip-flop, JK flip-flop, and then you can be ahead of my lecture in the class. Okay, so this is how you learn ahead of the class by doing some self-learning online. So I think I will want to stop here because we've learned something on the flip-flop today. We've learned what is the difference between the flip-flop, and I'll keep the rest of the material for our class next week, and then just so that we can be in line with our syllabus progress. Okay, so is there any question for today's class? So today's class is a short one, so it's barely 1 hour since we started the class. And today's class we've learned about flip-flop. Any question on flip-flops before we end our class today? So if there's no question, then feel free to get the attendance if you came in late. And if you have any question, you can stay back, and I will try my best to explain to you in a way that you can understand. Okay, so I wish you all the best. And it's the end of November already, and we are going to march into December, I think, in a few days' time. So I really wish everyone a good time, a good weekend. All right, take care, everybody. See you guys.
Thank you, sir. Have a
Thank
good
you,
weekend,
sir.
sir.
All right. So any issues, please stay back. If you have any problems, any difficulties, also, yep, please feel free to let me know.